Uh, yes, CRS depend on orientation. Means the critical resolve shear stress is different for different slip systems. So one slip system in one grain that represents a single crystal yield strength means that CR for CRSs. Can you hear me? Arvinda, can you hear me? Yes. Okay. Isn't CRS is fixed for slip plane? Yeah, so for a slip system, it is fixed. So, means generally we use the polycrystal materials now. So, for single crystal, CRSs will be a single quantity, means that will be constant. But for polycrystal materials, the CRSs will depend on orientation for different grains. So, yes, CRSs is fixed for a slip plane, and that depends on the angle with no, that is the result shear stress. Resolve value shear stress and critical shear stress, same thing. So resolved shear stress is a condition where the tensile axis angle and the slip plane normal and slip direction form a orientation which favors the deformation of the material. So that deformation will occur only when that increases to a increases means that sorry surpasses the critical shear stress value. So critical shear stress value for a single crystal is fixed. So when we apply stress, so when resolved shear stress reaches more than critical value, then that deformation will occur. So the resolved shear stress is only for a given condition, and critical resolved shear stress is fixed for that crystal. Okay, let me share my screen. The answer was given CRCS depends on orientation. Would that be a correct statement? Yeah. So CRCS depend on orientation. Means for a material means for different planes there will be different slip system na so it is constant for one single slip system and different for means if we consider more than one slip system then that will depend on orientation. So in the question it is asked for the a bulk material. So can you see my screen? Okay. Okay, then, so in the week 9 lectures, the professor taught about the strengthening mechanisms. So he elaborated about the precipitation hardening in the aluminum alloy. Okay, so I will go through the example questions for that. So the first question is that consider a precipitation strengthened aluminum alloy. After an appropriate heat treatment, the microstructure of the alloy consists of precipitates with a mean spacing of zero point 0.2 micron. Compute the shear stress required for or one bowing of dislocations in this material. So the Orovan, there are two cases where when the dislocation shear or cut the material, or otherwise uh, the dislocation bow around the precipitate particles. So when the precipitate size is small, yes. So जो Athar, can you see my screen? Okay. So the in the week 9 lectures, the professor taught about the strengthening mechanism. Have you reached up to that, or you are still on the week 7 or 8 lecture? Still on week 8. Yeah. So in the week 8, we studied about the dislocation interaction. So now today we will discuss about the strengthening mechanism. So strengthening mechanism by the dislocation, by interaction of dislocation with the different microstructural features in the material. So the microstructural features can be second phase particle, interstitial atoms, solute atom, which is different from the uh, sorry, a solvent metal. Like if we add two metals, so the solute metal atom will affect the strengthening of uh, uh, the primary alloying element. So the interaction between dislocation and those particles, or it means, so I will write it here, like the interaction of dislocations can be with, first is the other dislocations, second is grain boundaries, third is solute atoms, fourth is precipitates, and fifth is dispersoids. So the interaction of dislocation with these five microstructural features result into different type of strengthening mechanism. Is the interaction of dislocation with these uh, features uh, result in strain hardening of the material, means is strain hardening, more dislocations will generate, or if the some so the dislocation density is increasing with interaction. So as the dislocation density increases, there will be two types of dislocation, mobile and immobile. So mobile dislocation will help in deformation, and immobile dislocations restrict the path of mobile dislocation location. So by restricting the path, the stress required for further deformation increases. So stress required for further deformation increases means the material got strengthened. So depending on these five features, there are five types of strengthening mechanism. So with when the dislocation interact with other dislocation, that result in strain or work hardening. With grain boundaries, it is grain boundary strengthening. Grain boundary also restrict the path of dislocation. So from solute atoms, the elastic modulus difference and the atomic or crystal mismatch result in the strengthening. So that will be solid solution strengthening. With precipitates, it is precipitation strengthening, means the precipitate which forms with quenching of the material from high temperature and aging, so that those precipitates also interact with this dislocation. And from dispersoids, it will be dispersion strengthening. Okay. Precipitate, yeah, I will give the precipitate example. Yeah, so the precipitate that they are intermetallics, means when two metal combine, so that results in precipitate, means like if we talk about aluminum copper system, aluminum having 4 weight% copper, so it is generally the 2000 series alloy. So the intermetallics from this system is Al to Cu. So two aluminum atoms form with one copper atom form a intermetallic. So this intermetallic particle is called as precipitate. Like and similarly for the uh, aluminum magnesium alloy, there are and aluminum magnesium silicon, there are M, Mg2Si intermediate precipitates. With aluminum zinc also they form Zn Zn precipitates. So the intermetallics are called as precipitate, and the uh, uh, if oxides and carbides are forming, carbides are called as dispersoids. So the dispersoids and precipitates also differ from each other. Means the dispersoids of like tungsten carbide, molybdenum carbide, vanadium carbide, and Al2O3. So when these particles form, they will be stable at high temperature. Uh, but so at high temperature they are stable, so they can still provide the dispersion strengthening. Means they maintain the strength of the material at high temperature. But if we talk about precipitates, so precipitates dissolve at high temperature. So their strength is only increased for a specific temperature, service temperature regime. So the precipitates have some service temperature region in that the strength is higher, but for dispersoids, they are stable at high temperature, so they will provide more strengthening in the metal. Okay, so the precipitation strengthening occur. I will explain here. Means so precipitation strengthening is can be understood by phase diagram. So if we draw phase diagram of temperature and weight percent of copper, so this is this is solidus line, this is liquidus, and sorry, this is liquidus, liquid, and here this will be liquid plus solid, and here it is solid. So we can see that at this point the concentration is let's say C1. So if we move on this line, so with decreasing temperature, if we mark a point, so we can see the concentration of copper is also decreasing in the aluminum. So this is the principal criteria for precipitation strengthening. Like, so first is the solubility should decrease with decreasing temperature. Okay. So in the this aluminum copper system, generally so the precipitates are formed by using a specific method. Like, for first we solutionize the our alloy to a temperature. So this is 660 degrees Celsius. This is around 500 to 400. So generally, we heat the material to single solid solution where the concentration of copper is higher, let's say at T1. So we heat the material first, heating to T1 to make a single solid solution. So means the copper and aluminum are uh, all copper atoms are solutionized in the aluminum matrix. So first is the heating, second is the we quench the sample to room temperature or a higher temperature, let's say T2. Sorry, quenching at low temperature. So when we quench the this alloy, so all copper are in will remain in the aluminum matrix. Means if we so quenching is the rapid cooling. In slow cooling, the copper will segregate from the aluminum matrix, but we but when we are doing quenching, so in quenching there is rapid cooling. So the rapid cooling remain helps in remaining the copper atoms in the aluminum matrix. So that solid solution is called as supersaturated solid solution. After that, if we heat the sample to a slightly higher temperature than T2, heat at a very low temperature, or it can be at 100 degree 100 to 150 degrees Celsius or room temperature. So depending on the temperature given, with the time the it is supersaturated solution. So when we keep it for long time, so with time the Al2Cu precipitates starts to form in the aluminum matrix. Means copper segregate and copper segregate in the aluminum matrix slowly and form this intermetallic Al2Cu. So that will be so with a solid solution we can see that this is the microstructure in this is completely alpha. So when we uh, keep the material for long period at high temperature or room temperature, so small precipitate particles will form in the grain grains and at the grain boundary also. So these tiny particles form with time in the aluminum copper system. So these tiny particles interact with dislocation, increasing the strength of the material. Al2Cu precipitate and the white space is the alpha solid solution with decreased amount of copper. Okay. So with there is one phenomena also. So with increasing the precipitate size, the strengthening mechanism also differs. Means the uh, small precipitate uh, can be sheared or cut by dislocations. So in this condition, when precipitates are small and dislocation can cut them easily, so the strength is given by the strength is directly proportional to square root of the precipitate size. And if precipitates increase in size with time, so the large precipitates cannot, so the large precipitates means they will get strong, so the dislocation cannot cut those large precipitates, so then the dislocations bow around precipitate and then surpass it. So in that condition the shear stress uh, will be proportional to inverse of the uh, precipitate size. And in this large precipitate also, mm, no, this is not the particle size. At the large particles, there is the distance between two precipitate particles. Means uh, at with small precipitates, the spacing between two precipitates will be small. So spacing between two precipitates is uh, small. But with large particles, that spacing will increase. So for large particles, the shear stress means the stress required for deformation is inversely proportional to the spacing of the precipitates. These two particles having lambda. So means the bowing of around precipitate we can consider as means these are the two precipitates and this is dislocation line. So dislocation is moving towards the precipitate. So at the second stage, it bow around like this. So the dislocation line tries to uh, move through the precipitates, so it bow and that results in further. This is the lambda distance. So some very small dislocation loop also starts to forming around precipitate with time. So at some point, the dislocation line escape from these particles, and these precipitates are surrounded by new dislocation loop, and this is the dislocation line when it surpasses from these uh, precipitates. So these small circles are the dislocation loops. So this dislocation loops can further result in uh, a generation of more dislocation. Means point of dislocation generation. Okay, so means dislocation surpass from the dislocation. After that, the dislocation loop is remaining on the precipitate. So these are the two mechanisms in precipitation strengthening, which increases the strength of the aluminum copper system. So, uh, this precipitate strengthening can also be found in aluminum magnesium silicon system, and aluminum zinc, and aluminum lithium also. So these and one more thing, aluminum and copper. So these are the precipitation hardenable series. And the remaining aluminum copper series, remaining series is like aluminum magnesium, aluminum manganese, they are strain hardenable, like aluminum magnesium, simple pure aluminum, aluminum manganese, these are strain hardened. So depending on the material or alloy, the strengthening mechanism will differ. In small precipitates, it is size of the precipitate. It is R. So with small precipitate, the particle size dominate, while in the large precipitates, the distance between precipitate dominates in strengthening. Okay, so we'll discuss the questions. So in this question, we have asked that consider a precipitation strengthened aluminum alloy. After an appropriate heat treatment, the microstructure of the alloy consists of precipitates with a mean spacing of zero point 0.2 micron. Compute the shear stress required for one Boeing of dislocation in this material. So we have given spacing between precipitates. So lambda is the zero point 0.2 micrometer, and it is aluminum alloy. So we have asked to calculate the shear stress. So shear stress can be written as GB by lambda. So the shear modulus for aluminum alloy is 72 GPa, and Berger vector is generally 0.286 nanometer. So when we put this value in this, so we can get the G is 72 into 10 raised to power 9 Pascal. into 0.286 into 10 raised to power minus 9 divided by lambda is zero point 0.2 into 10 raised to power minus 6 meter. So this will get cancelled out and that will give, uh, sorry, here G is the shear modulus, not the elastic modulus. So G is shear modulus. So for aluminum, it is 30 GPa or 27 also there. So elastic modulus is 72 GPa for aluminum and shear modulus is 30 GPa. So when we put here 30, so that will result in 42.42 into 10 raised to power 6 Pascal. That will be 42.42 megapascal. Okay. Next, next question we will solve. So it is a theory-based question. Means the steel all means we discussed that different materials will have different type of strengthening mechanism. So in steel also we have a strengthening mechanism which results in increasing the strength. So steel is one of the most important engineering materials. Consider the different strengthening mechanisms and make a list of different contributions to the strength of low carbon steel. So in the low carbon steel, it is steel means it is iron and carbon, but some other trace elements can also be there like magnesium, silicon, tungsten, chromium, vanadium means very stress amount. So these all can form carbides with with carbon and with contact oxygen they can form oxides also. So there are dispersoids. So first the first contribution in steel is the lattice friction stress. Means lattice friction stress is the compulsory strengthening in any material if we don't have any dislocation or any other feature. So lattice friction will always be there. So we can say it is pulse Naviero stress. Okay. Second strengthening is the solid solution strengthening. It is written as sigma k root C. So C is the concentration of solute. Means the carbon percentage here and K is the some constant. So with depending on the carbon concentration and some other element which influence the strengthening with its presence, so that also results in the solid solution strengthening. Third point is the dislocation or strain hardening. Means if we provide some deformation to the steel, so that deformation also increases the dislocation density, and that dislocation density increases the strength of the material. So here the stress is given as alpha GB square root of rho. So alpha is some constant, G is shear modulus, B is Berger vector, and rho is the dislocation density. Next is grain size strengthening. So the grain boundaries also restrict the dislocation path, so that results in the strengthening. It is given as sigma equals to K by root D. So D is the grain size. So with increasing grain size, the strengthening will be low, and with if we have a finer grain size, so finer grain size will result in more strength. Fifth contribution is from precipitation hardening. So precipitation hardening in a steel results from the carbides of iron, niobium, titanium, and vanadium. So the carbides forming from these elements that results in precipitation hardening or dispersion hardening also. Okay, so next question is on the an overage precipitation harden. So overaging is the means if we draw a curve between hardness and aging time. So uh, we have some small amount of hardness in the material. So the hardness increases with aging time, and it achieve a maximum hardness for a aging time. So this is called as the peak aged condition. So the in the peak aged, the hardness is maximum, and the stage before this is the called as the underaged, and stage after peak aging is called as the overaging. Okay. So in this question, we have asked that an overage precipitation hardenable alloy has a yield strength of 500 MPa. Estimate the interparticle spacing in the alloy given that shear modulus 30 GPa and Berger vector 0.25 nanometer. So we have given yield strength 500 MPa. So the shear strength of this alloy can will be half of the yield strength. Means yield strength is in um, the load the means the normal strength, and the shear strength of this alloy will be half of yield strength. So 500 by 2 will be 250, and we know that the formula is GB by lambda. So we have to find the interparticle spacing. So lambda will be GB by tau, So G is the 30 GPa, B is 2.0.25 nanometer. So 10 raised to power 9 and 10 raised to power minus 9 will be cancelled out. And we have given a strength of 250 megapascals. So it is 10 raised to power 6. So when we calculate this means 30 into 0.25, so that will result in 10 raised to power 2 and 25 will get cancelled out. So at the bottom it is 10 raised to power 9. So it is 30 into 10 raised to power 9 meter. So this will be 30 nanometer distance interparticle spacing. Okay. Uh, Pulse numerical stress and the energy curve. Okay, just yeah. So pulse numerical stress is the lattice friction. Means we have atomic arrangement like this. So when the top layer of atoms move in this direction, so the atom should have to come here. So the energy curve, energy will increase when it comes at this point. Okay. So when the atom moves to this position, so the energy will increase at max and maximum will be maximum at this point. When it reaches here, the energy again decrease. And if we move here again, so yeah, so for this point, it means the when it come here, then the position will be same as previous with no stress. So when we uh, plot force for this same range, so this would be R by 2. This is R. So the force in the so the energy curve will get divided into four positions, four parts now. So at this 1/4 position, the force will be maximum and it decreases when it reaches at it this point and it will be very low at this position and it follows the means the force will get again zero with the when it reaches at this point. Okay, so force we can write as shear stress tau. So it is directly proportional to sine of this r, and if we calculate it, so it is generally depend. So some calculation is there. So means the energy curve follows like this only. So that will be some pulse stress formula is given by tau Pn. It is 2g divided 1 minus nu exponential of minus 2 pi w divided b. So B is the G is shear modulus, nu is Poisson's ratio, B is Berger vector, and W is the width of the uh, dislocation. Means uh, okay. So at the top side there are five line, and at the bottom it is four line. So the dislocation width which we discussed in the previous lectures. So that W is the this dislocation width. So in dislocation also we have atoms. So when it moves, so that friction means the friction stress felt by these atoms during the motion of dislocation. So that will be Peirce-Nabarro stress. So you can see derivation for this Peirce-Nabarro stress in the textbooks also. Okay, so we'll discuss the assignment questions now. Yeah. Okay. So, first question asks that dislocation can interact with which of the following microstructural features? So, we discussed in the strengthening mechanism which features are responsible for dislocation interaction. All of the above, yes. Next question. Which of the following statements are correct for precipitation with respect to time? So, option 1 and 2, yeah, precipitate size increases and distance between precipitates changes. First and third question is which of the following are basic requirements for precipitation strengthening? So we had discussed in the phase diagram like solubility with when we decrease the temperature, solubility also decrease. So first option says it correct means solubility should decrease with decreasing temperature, and second is wrong. Formation of supersaturated solid solution. So this is also required. and presence of a single phase region at high temperature. So this is also correct. Okay. So next question. So fourth question is, yeah, third question is, a single phase alloy can be strengthened by which of the following mechanisms? Single phase alloy means there will be no precipitate or dispersoids. So other than dispersoid and precipitation, what can be the strengthening mechanism? So there are two options remaining: solid solution and strain hardening. Okay. So next question is, which of the following conditions favor dislocation cutting of precipitate? So when dislocation cut the precipitates, yeah, one more thing I have to tell. Like with increasing the size of the precipitate, the interface also changes. Means for small particles, so small precipitates, the interface of the means aluminum matrix and precipitate is coherent. Coherent means atom to atom matching. Like I will show a picture. Yeah, yeah. So Can you see this picture? I will zoom out little bit. Yeah. Yeah, so in this picture, the A figure shows the complete lattice matching. Means the same crystal structure can be seen in. So this is circle, small sphere is the precipitate, and outer of this is the matrix. So we can see that the atoms are matching very uh, means atoms are aligned one by one. So this situation we can say as the complete coherency. So there will be no strain between atoms in the for the first figure. In the second figure, the atomic spacing between two atoms is decreased from the as compared to the aluminum matrix. So in this, the atoms are still matching but have with some strain. So the second figure represents the coherency with strained but continuous lattice planes across the boundary. Means lattice planes are matching but with having a strain. Next, third type of situation says that atomic spacing is completely different, and the atoms are matching for some planes, and some planes are not matching with the matrix and the precipitate. So this can be means there is still some atomic matching. So this third figure we can see as semi-coherent interface. So this is semi-coherent partial continuity of lattice planes across the interface. In the fourth picture, there is complete mismatching of the atomic arrangement inside the precipitate and out in the aluminum with the aluminum matrix. So the D figure is written as incoherent equilibrium precipitates which have no continuity of lattice planes across the interface. So these four types of interfaces are found in the precipitation hardenable alloy. So with time, we can see, so this is at time T1 when precipitate starts to form. This is at T2, this is at T3, and this is at T4. So as time progresses, the coherency between atoms decreases. So at the last stage where the material is overaged, so that will result in incoherent precipitate interface. Okay. So now we can solve this fifth question. So it is asking that following condition favor dislocation cutting or precipitate. Yeah, so this when so dislocation cutting will only happen when coherent interface is present between precipitate and the aluminum matrix, and the small when the precipitate size is small. So first and second option will be correct for this. Is it clear? Okay. Option 3. Okay, we'll go to next question. So in the sixth question, we have asked that An alloy containing 4 atomic percent of beryllium initially has a coherent precipitate size of 10 nanometer. During aging, the strength increases from 200 MPa to 550 MPa. Assuming the precipitate remains coherent, determine the precipitate size after aging. So means the precipitates are coherent, so the dislocation, precipitation, cutting or shearing mechanism will dominate in that region. So during the shearing or cutting of precipitate, the shear stress is directly proportional to precipitate size R, square root of R. Okay, so we have given, so we need to solve precipitate size after aging. Initial radius is 10 nanometer. So R1 is 10 nanometer, toy 1 is 200, R2 we have to find, and toy 2 is 550. So we can take a ratio. Toy 2 by toy 1 will be root R2 by root R1. So we have to find the radius. So R2 will be tau 2 by tau 1 square into R1. So that will be 550 by 200 square into 10 nanometer. So that equals around 75.6 nanometer. So the first option is correct for this. So you have to solve this like this, means ratio by taking ratio and then equate for 1. Okay. So coming on seventh question. An alloy has an average precipitate spacing of 2 micron and strength of 200 MPa. After aging, the spacing increases to 4 micron. Assuming dislocation bypass the precipitate, determine the alloy strength after aging. So in this question we have given precipitate spacing and dislocations are bypassing the precipitates. So it is written as means shear stress is inversely proportional to spacing. So we need to find alloy strength after aging. So that will be toy 2 by toy 1 will give lambda 1 by lambda 2. So toy 2 can be written as lambda 1 is 2 by 4 into 200. So that will result in 100 MPa. So the B option is correct for this. Next, eighth question. Which of the following statement regarding solid solution strengthening are correct? So in the solid solution strengthening, there will be two types of solute atom. One is substitutional, second is interstitial atom. So the substitutional atom have spherical distortion field around it that interact with dislocation, and interstitial solute atom have non-spherical distortion field. So the first and second option is correct for this. Next is stress field around solute atom interact with the dislocation stress field and increase strength. So this the third option is also correct. Means the interaction between dislocation field in sorry stress field around dislocation and solute atom result in strengthening. Fourth option, it is saying the interstitial solute atom provide strong strengthening than substitutional atom. So this is also correct. Interstitial strengthening will be higher than substitutional. So the uh, okay. Next question is which factor increases solid solution strengthening? So the solid solution strengthening depends on the concentration of the solute atoms. So, and it depends on the size difference also. So in this question also, all four options are correct. Means size difference results in solution solid solution strengthening, elastic modulus difference, uh, high solute concentration, and yeah. So this decrease in no third only first three options are correct. The fourth is wrong. Okay. So some more questions are there. No, we have solved them. So these questions are from the previous assignment. So some questions are same as the new assignment. So in this we have asked the dislocation can interact with. So in this all four options are correct. Dispersal, green boundary, solute atoms, and dislocation. Second option also is same. Second option is which of the following statement is correct for precipitation with respect to time? So precipitate size increases and distance between precipitate changes. Third question says a single phase alloy can be strengthened by solid solution strain hardening. Fourth option is the favorable condition for the dislocation to cut the precipitate are so it is so small precipitate and coherent interface. Fifth question is so it is different. So under tensile loading, a 2x series aluminum alloy failed in an intergranular manner after heat treatment. One of the most suitable reason include yeah. So intergranular manner fracture happens in this aluminum copper system when we slow cool it from high temperature. In quenching, it is means there will be ductile fracture, but for the slow cooling leads to intergranular fracture. And quenching doesn't. So from the options, we have that 2000 series aluminum alloy is intrinsically brittle. This is wrong. Second option says alloy was solutionized followed by quenching, which results in supersaturated solution. This is also wrong. Uh, Alloy was solutionized followed by slow cooling, which resulted in the formation of precipitate at the grain boundaries. So, because of the precipitates are forming majorly on grain boundary, so that result in uh, intergranular failure. So, third option is correct. And alloy was solutionized followed by slow cooling, which resulted. So, the fourth option is same as third. Okay. So, next question is same as means we have to find the precipitate size after aging. So it is same as means tau it equals to square root of no, mm, R2 by R1. So from this the R2 will be 75.6 means we this calculated it in the previous question. Second, next question is mark the correct statement. So in this first option says dispersoids are suitable for strengthening at high temperature. So it is correct means dispersoids are stable at high temperature. So first option is correct. Precipitates are formed from the matrix. Yeah, so first we make the supersaturated solid solution and that will result after aging precipitates are formed from the matrix. Third option is says the interface between dispersoids and matrix is incoherent. Yeah, this is also correct. The interface between dispersoid and matrix must be coherent. So this is wrong. So A, B, and C is correct. Okay. The whole ticket I don't know. You can ask in the portal also, so they will help. Okay, so you cannot see. I will increase the font. Can you see it now? Okay. Yeah, just going to question. Okay. So eighth question, we have asked that an alloy has an initial average spacing of 2 micron and strength of 2 MPa. After aging, we have to precipitate spacing is 4 micron and assuming dislocation bypass the precipitate, determine the alloy strength after aging. So it is same as in the previous. So the strength is inversely proportional to interparticle spacing. So the tau 2 will be lambda 1 by lambda 2 into tau 1. So that will give 2 into 200 by 4, that will be 100 MPa. Okay, so the B option is correct for this. Again, the next question is which of the following statement is correct? Uh, so it is asked for the substitutional solid solution strength, sorry, solid solution strengthening. So it is same as the previous questions. Like substitutional atom has a spherical distortion field. It is correct. Interstitial has non-spherical distortion field. Second is also correct. Stress field around solute atom interact with the stress field of the dislocation, lead to increase in strength. So it is correct. Interstitial solute atom provide more strengthening compared to substitutional atom. So this is also correct. Next question we have asked, like which of the following statement is correct regarding the stress strain curve obtained by uniaxial tensile deformation of mild steel? So this question is regarding the strain hardening behavior. So I just uh, ma- uh, uh, tell means in the mild steel, the tensile stress curve looks like this: sigma versus epsilon. So this in the mild steel we get two yield point. So first is called as the upper yield point. This is lower yield point, and this is tensile strength. Okay, so in this the stress strain curve exhibit yield point phenomena. Means we can see the yield point clearly in the steel tensile stress strain curve. Upper yield point is due to the formation of quadral atmosphere. So quadral atmosphere is the solute atom with dislocation. So that condition from a quartal atmosphere that show some strength at during the tensile testing. So first and second is correct. Third option is formation of lower yield point helps to maintain the constancy in strain rate during the deformation. So this third point is also correct, means this is required to maintain the strain rate. Okay, so first, second, and third is correct. Fourth option it says Luderband formation can be seen in the whole gauge length of the tensile specimen after the uniaxial tensile deformation. So it is also correct. Means if we have a dog bone sample, sorry, this my system is lagging today. So these type of dislocation line are formed on the tensile specimen of the mild steel at the gauge length. So that's why these bands are called as the Luder bands. Okay, so all four options are correct in this. Means the dislocation lines are formed uh, at 45-degree angle on the tensile specimen gauge length. So these dislocation line in a group are called as the Luder bands. Okay. So do you have any other doubt? Means questions are completed for today. So if you have doubt, you can ask. Okay. So we have three more sessions, then the course will get over. Okay, so then we'll meet in next week. Thank you.